What's up? Hello, it's me again, Carson. Welcome back to Stat 3050 at the University of Wyoming, still online and still having a good time. I'll tell you what. I hope that's not getting old, because I feel like I've been saying it now for years. I know it's only been a couple of months, but, whatever. Okay. So today we are working in multiple regression still, but we've got a categorical predictor, just one, but it's got 3 levels, okay? So the concepts still mostly stay the same. The computer treats it just a little differently, and we have to do a little bit of thinking, our way around it, but it's all pretty similar. Also, just a quick note, this example is with 3 levels, but the same concept applies to a categorical predictor or predictors with 4 levels, 5 levels, some amount of levels, just more than 2, right? So it's the same thing. We're just doing 3 for ease of learning. Cool. Okay, so per usual, I've got some goals. I want to make a little fancier plots with ggplot2. Nothing too crazy, but stuff just to make it a little bit easier to see what's going on, a little easier to tell the story, that kind of thing. And then I want to introduce reference levels when there's more than 2. In this case, that would be 3. so that's good. And then I'm going to show you how to relevel factors. That'll make a little bit more sense once we get into it. But releveling just means that we're going to change the reference. So that's all cool. And then again, per usual times 2, we've got this example brought to you by just normal music. Earth Tones by Bahamas, pretty good. Normal music isn't bad. In fact, both these albums are pretty good. But every time I listen to these albums, I'm just like, you know what? It's pretty normal. Same thing with Dr. Dog, Shame. So good. That album I think it has like 20 songs on it. It's super long, but it's pretty good. But it's pretty normal too. So, all right. So enough of that. I'm going to move on to a bit of an example, something a little different than we're used to seeing, but it should make this idea of reference levels a little bit more clear. So let's get into that. All right. So here we are. This is a map of what hopefully looks familiar. It's a map of Albany County and a little bit of Carbon County too. But it's Laramie, pretty much everything west of Laramie up into the Snowies. And you're probably wondering, Carson, what the heck is this? Well, I'll tell you what the heck it is. We've got 3 different places, right? We've got Laramie, our nice home over here. That's downtown, picture I took a little while ago. And then we've got Jelm Mountain-ish over here in Albany, the little town. That's at about 10,000 feet. Laramie over here is about 7,000 feet. I'm rounding to make math here in a second easier. And then we've got Medbo Peak. Very pretty. Gosh, so nice. And that's at about 12,000 feet. Okay, so this idea of reference levels. Okay, so we right now are looking at this from a bird's eye view, right? We are able to say, okay, we know that Medbo Peak is at 12,000, Jelm is at 10,000, and Laramie is at about 7,000. That makes sense, right? But when we're standing in one of these places, we have that place as a reference. Okay, so let me actually have a model here, not a statistical model, but a practical model. Let me bring him in. Bubba! There he is. Okay, cool. So there's Bubba. So let's say that Bubba here is standing on let's see, that's Grand and Second there. He's now standing on the intersection, and he's looking west. He is 3,000 feet below Albany here, and about 5,000 feet below Medbo Peak, okay, with reference to Laramie, okay? So with reference, he is, about 5,000 feet away, I guess underneath Medbo Peak, and 3,000 underneath Albany, right, or Jelm here, okay? And then we move Bubba now to Joan. And now he is 2,000 feet below Medbo, but 3,000 feet above Laramie with reference to here, right? So the difference in distances here would be, let's see, I guess like a negative 2,000 feet between Bubba at Joan and Medbo Peak, and then a positive 3,000 feet between Joan here and Laramie, right? And then we move Bubba again. Bubba! And now, Bubba is above everything. And he definitely thinks that. He's got that kind of attitude, you know. He's always up here sitting at 12,000 feet. But now he's 2,000 feet above Albany, right, above Joan, and 5,000 feet above Laramie. Okay, so with reference to Medbo Peak here, right, he's a positive distance above everything else, right? Put him back in Laramie, and now all of these values are negative, right? The distance, or at least the difference in elevation here is a negative 5,000 feet and a negative 3,000 feet. If we're saying, you know, Laramie minus this or whatever. Depending on how you frame it, it might be a little different as far as the sign goes, but we can kind of get an idea of wherever you're standing, right, is what you are referencing, right? So with reference to Medbo Peak, you know, we've got positive, 2,000 and 5,000 feet. Same thing here. We've got a negative 2,000 feet and a positive 3,000 feet when with reference to Joan. And then again, you know, we're 3,000 feet below Joan and 5,000 feet below Medbo. Okay, so let's keep that concept in mind when we move into this next concept in R. Say goodbye to Bubba. Of course, he lives in our hearts all the time, but we're gonna leave him behind now. We'll put him back up here because that's where he thinks he belongs. All right, let's get into R. Sweet. So here we are. Per usual, R looks the same. It's probably never going to change. Okay, so today we're working with a data set that is from the class Excel, except the one in the class Excel is like a truncated version of it. It's not the whole data set because I want to use the whole data set now in this example. So we're working with jellyfish measurements and the location from where they are sampled. Okay, and this is all outside of Australia on a couple of islands here and there. I'll show you actually here in a second. So let me actually set my working directory. I've got my data stored in Categorical in my multiple regression folder, so that's all right. And then I could copy and paste that output, but for this I'm not too worried about it. So I think I just have the data set called Jelly. I'm gonna call it Jelly. And then it's a CSV file. And I'm pretty sure it's just called jelly.csv. So we read that in. Yeah. Cool. So we've got three different things here. Okay, we've got a width measurement, we have a length measurement, and then a location. So we've got Dengar Island, we've got Fraser Island, like the TV show, and then Salamander Bay, like the amphibian, denoting these three different like sampling locations. Okay, and then we've got length and width. Not really too sure what the measurement units are, but it doesn't really matter so much for this example. And our goal is to figure out how width and how this location are related to length. Okay, we're not trying to predict. If it so happens that we can, great, but that's not our initial goal. That's not our primary goal. So this is going to be predictor 1, right, a continuous variable. This is going to be predictor 2, and it's got 3 different levels, which we can see there. Okay, cool. So let's run that summary function on Jelly here, just to kind of see what's going on. So we see that we get the 6-number summary for each of the continuous variables, and then the sort of counts for the locations, and we see that, okay, so there are more jellyfish sampled at Salamander Bay. Not a huge deal because we got decent numbers for both. of the other places, Dangar Island and Fraser Island. And then, so that's all good. And then we saw it when I hovered over the column, but let's run that structure function just to make sure that everything is being treated as appropriately. Okay, so we've got two numbers here, two numeric variables. That's good. I think they're rounded off to the half here. Yeah. So you have 6.5 and then 6, right? There's nothing in between. And then the factor here with 3 levels, Dangar Island being the first level. So we can kind of see that there. It turns out that by default, it's going to use that as the reference level. Okay. We'll get to that in a second. Not too worried about it right now in this moment, but we will in just a little bit. So let's get into some plotting. Let's get into some plots. So we'll read in. Oh Lord, we'll read in the old tidyverse here. Handy dandy. And that's got the ggplot function in it. So we'll go ahead and we'll get our base kind of layer down. So our predictor for right now, our numeric predictor is width. And we're trying to see how that's related to length. And it's all caps too, I think. Or first capital letter, yeah. So if I run that, nothing will show up. I'm not going to run that because I don't want to have to... Editing these videos, kind of takes a little bit. So I'm trying to slim that time down. Anyway, so we've got geom point and then geom smooth. smooth. With the method equals linear model. And I'll clean up the background here too. Cool. Zoom that in. What do we get? Okay, so we get a fairly basic looking scatter plot where it's decently positive, right? There's pretty good evidence that there's no curvature, so that's good. We can model this linearly right now at least, and we'll be set. But what are we missing? Well, we don't really see the 3 locations. Okay, so we only see width and length in general. Okay, so how do we go about making this figure include more information? Well, great question. We can go into this aesthetics function here on line 16 through 19 and kind of fiddle around with it. So if I make a new argument, and it's called COL, it's part of the aesthetics function here. COL is short for color, and I could put in location, and let's just see what happens. So zoom that in. Awesome. Sweet. Look at that. So that is now making a regression line for each 3 locations and coloring the dots differently too, which is pretty rad, right? So what are we looking for here? Well, the biggest thing initially is to look and see if the slope of the lines are at least similar. They don't have to be completely identical visually, but they should be at least, remotely close. So that's, and it looks like it is true here too. Okay, so just a quick note though, when we model this, we're not going to be, the slope that we get is not going to be for each of these individual parts. We get the general slope, right? Because remember that in linear regression, we calculate things by holding the others constant, right? So we're still going to be able to model width and length, but we are going to be able to include the different locations too. Cool. And then another note, if for instance we had one of these lines, was negative or totally flat or like very much different than the other two, then we would have to go in and either kick that out or do something a little different with the analysis that we're not going to get to this week, but we will next week. Cool. Okay, so you turn this in to your advisor or whoever, your boss or your lab mates, and they say, okay, I like that, but I still want to see the general trend, and, I don't want it to be too busy, because it's so easy to make plots that are like uber busy, right? So we're going to try our best to get around that. All right, so how do we include the general trend? Boy. Okay. How about we do this? How about before this geom smooth here, this first geom smooth, maybe we make another one and see what happens? And then we'll do method equals lm again, just to see what's going to happen. Huh. Well, that did not do what I wanted it to do. So let me get rid of that. What do I do? Okay, so it turns out that this aesthetics function here in the whole ggplot, right? This is more or less sort of the foundational, everything that goes in this aesthetic function here will be mapped in all of the consecutive components of the function, okay, or of your code here, making this figure. So I want to get rid of this color, and I want to put it in the other components. So it maps it separately. It will still look the same. But it's going to be treated just a little differently. So in the geom point, if I put this AES, again, aesthetic, and I put that color in there and run that, what's going to happen? Zoom that in. Okay, almost, right? Almost. We've got different colored points now, and the general trend, so that's all right, but maybe I want to keep in those individual slopes at the different places and include the new trend, right? Or not the new trend, the overall trend. Okay, so how do I do that? Well, let me move this color. I'll keep it in the geom point, and I'm going to copy and paste it into the geom smooth here. Let me run that, and we're kind of back to where we started, right? Which is good, which is fine. We're like almost there. Okay, so now we have a little bit more control with the nitpicky kind of components. Okay. So I've got geom point, I've got geom smooth, and it's all looking decent, but I still want that general trend. It turns out that you can pretty much put in as many different components as you want, and they'll just layer them on top of each other. So if I just put in this geom smooth with nothing else in it, it's going to be mapped in the same way that is called here. Okay, so if I run that, what happens? Shoot, I forgot. Okay, so I forgot to put the the method equals lm. So this is drawing that lowest line. Here we are at a very busy plot, right? What's the issue? 3, kind of. The first one being we want a straight line, right? The second one being that this blue that's by default in R is super similar to this blue, right, for the Salamander Bay. We could go in and change the colors manually of the locations. Don't want to do that now because, one, these colors I think are colorblind friendly, which is pretty cool. And I don't know, enough about how I want this figure to look, so I will just stick with the defaults for now. And then the other thing is that this line here, our general trend, has that confidence band. It's kind of overlapping with the other ones, so either we could get rid of the other ones, or we could get rid of the other confidence bands of these 3 individual lines, or we can get rid of the confidence band for the overall trend. I'll show you how to do both. It's not super difficult. So the first thing we want to do is let's go ahead and change that first issue. Run that. So that first issue being the lowest line. Zoom it in. Here we are. So it's looking a little bit decent. It's getting there, right? It's getting there. So then let's say, let's get rid of the blue and change it. Okay, so still the same deal. It's still going to take this color argument, except now we can just put in quotation marks whatever color we want. We could do pink, run that, and then now, we see we get this pink line. This is very busy, right? This is a lot to look at, and the pink is kind of faint too. So it's a good idea to use more neutral colors for those general trends. So using like a gray or like a beige or something like that is fine. So I've put gray in quotation marks here. I'm going to run that. And here we are. So it's gray. It's being a little bit sort of construed by the, or lost in the confidence band here. So let's get rid of the confidence band. How do we do that? Well, there is a function, sorry, not a function. I keep getting that confused. So annoying for you and definitely for me. Anyway, there's an argument in here called SE. And that's it. And it's a Boolean, right? Or a logical. So with that, it gets either one option or another option, and that's it. And those two options are true or false. So we'll put in false because we don't want it to be plotted. We'll run that. And look at that. Already it's looking a little bit better. It's looking a little bit better. And then we've got everything that was on my list checked out, right? But I don't like how that's the same sort of aesthetic as the other three lines. So let's make it a dashed line so we can see a little bit better. We could do line type and then in quotation marks dashed, right? That's pretty easy to translate into English. So we zoom that in again, and now we see that the general trend is now this sort of dashed line, and it looks fairly decent. Okay, you give this to your advisor or your boss or whoever, and they say, okay, that's fine, but I care more about the general trend because that's what we're gonna be modeling anyway. It just so happens we have these other three locations. Let's kind of flip the aesthetics around. Let's make the general trend the main feature and the three locations sort of the secondary feature. So let's make these three lines dashed. Let's make them a little bit less busy, and then we'll have a decent idea of what's going on. Okay, so you say, okay, boss, thanks. We'll leave color. Let's make the color black actually, so it sticks out a little bit more. And then we'll get rid of the SE, and then we'll just put that in the this other geom smooth. So this is now the geom smooth for the three lines, because we know we've got the color set for the location. Okay, so the SE is going to be false, and then the line type will be dashed. Let's see what that looks like. Pretty decent, I think. We've got the confidence band for the general trend, and then we have these sort of three. we have these three lines here denoting the three places, right? I think this looks decent. We can even, if we wanted to, this confidence band here is a little kind of opaque. You can change that. So we can just go into the general term here. For the geom smooth, for that general trend line, and we can use this function, this argument, good lord, called alpha, okay? And so that gets a value anywhere between 0 and 1. So if you put in 0 here, let's see what happens. Zoom that in, cool. So 0 makes the geom smooth, that band there, that confidence interval band, more, well, completely transparent, right? It's totally invisible. And then we can go in and change this to pretty much anything. I think maybe 0.2. Let's see what happens. See what that looks like. Yeah. So that's a little bit, more transparent, a little bit lighter, whatever. And it looks decent. I think, let's see just what happens, just for fun. If we put in like a really large value. Yeah. Cool. So I put in 5 there. The actual function, the actual argument can take any value, and the larger the value, the darker it gets, the more opaque it gets. The recommended, range is between 0 and 1, a little bit bigger than 0, maybe, and the default is 1, okay? So, gosh, if we put in like 100, let's just see what happens. Yeah, okay, so it kind of caps at a certain darkness. But anyway, just getting kind of finicky here, so I'm going to leave that at 0.2. And last thing was just zoom it in. And that's all good. I think it looks decent, right? we get a pretty good idea of the different slopes for the different locations, and then we've still got that general trend. So this is the line, this black line here is the one that we're going to be actually modeling, and then we can already kind of see that on average, these different places may or may not have some kind of effect on length, right? So the Dangar Island here might actually be, on average, a little bit lower than, let's see, Salamander Bay. Interesting here, though, is that Salamander Bay intersects the general trend here. So that might have something to do with it, too. Anyway, let's move on from this, and let's get into modeling. Okay, so per usual, let me give myself some more room here so you can see. Let's just include everything, and we'll do that. We've seen this plenty of times now, so I'm not going to get too worried about being too slow or too fast or whatever. So it's length, that's our outcome, as a function of width and location. And then the data is jelly. Okay, so I am losing my mind. I'm sorry if you think I'm going crazy, because I am going crazy. I've been inside now for I think 3 years now. Okay. So here we are. Residuals. The 5-number summary looks decent. The median is pretty far away from 0, so we'll get into that. We'll actually plot them. So we'll just sort of ignore this for now. This is not alarming, but it is, brings up some questions. We've got the coefficients table. Everything here is statistically significant except for Fraser Island here. Hold up. Location, Fraser Island. Location, Salamander Bay. Hey, where did Dangar Island go? I'm confused. What's going on? Okay, well, let's ignore that for now. We'll address that later. And let's check out the residuals here. So we'll bring in the GG Fortify, and that has that autoplot function. I can't type today. The object is model. The smooth color is nada. That's what NA is short for. And then the theme, classic, to get rid of the background. Zoom that in and see what's going on. Okay. Okay, so what's our first assumption? Well, we want to check to see if the residuals or the data, depending on how many dimensions we're working in, can fit a straight line. And it seems like it's fairly decent. And then we're looking for equal scatter. I would say that there's unequal scatter here. It's kind of hard to tell, but it's fanning outward just a bit, enough for me to be a little bit questionable of it. So we've got that. The residuals versus fit, not great. They're not horrible, but we might be able to kind of fix that up a little bit. And then the QQ plot here is looking a little kind of wonky. Towards the tails of this plot, you always have something that kind of goes out there, but you want to look for this kind of thing. You see how it's kind of almost sinusoidal around the middle here. Let's check out the histogram just to see what that looks like. And hist of the resid, the model. Okay, zoom that in. We've got, if we change the bin size, maybe it would look better, maybe it wouldn't. But here it's a little funky. It's kind of right skewed. We don't have a whole lot over here, but a decent amount of residuals on the other end. And then with all of that, if we go back to the model, we also don't have totally significant p-values. And our purpose is to relate, right? We're not trying to predict, so we don't really care so much that the intercept here is statistically significant, but we do care that at least we're trying to get these locations to be all significant, so we can at least say something. Now, it turns out that we could log transform the outcome to make this look a little bit better. So let's do that. And before you go on and say, like, Carson, aren't you kind of, cherry picking the data here, trying to make it say what you want? No, not necessarily. I would be if the residuals looked fine in this case. We could log transform still, and they probably will look a little bit better, maybe. If, for instance, they didn't look good, and I log transformed, but everything was all the variables were still statistically significant, well, then I would be sort of ignoring the obvious, right? So you can have a bad model and all of the p-values be statistically significant, which in this case, this is a decent model. The residuals look okay, but I think we could do better. So let's do that. So I'll call this model 2, and it's going to get this out of the way. A linear model where the formula equals, we'll do the log of the length here as a function of, is that what it is, length? Yeah, as a function of width and location. I'm also just, since there's only 2 variables, I'm just going to type them out. I could replace this with a period, but it might be that I would need to log transform the width here. Nothing too crazy. So we'll just leave it like that. And then the data is jelly. Okay, and then summary of model 2. See what this looks like. Okay, cool. So decently better, I think. The residuals a little bit closer to 0. We are now on a slightly different scale because we've log transformed the outcome, but that's all right. That's okay. And then we come down to the estimates, and then look at that. Everything here is statistically significant, so that's decent. R squared is not much different than the first model that we made. In fact, I think it's close to the same. Yeah. Of course, you're not really supposed to compare the R squareds when you're now measuring something different, essentially. That's fine. That's totally fine that the R squared here is still decently high. And then we'll go on to the residuals. Blah, 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 blah. Losing my mind. Cool. Run that, and let's see what happens. Cool. Okay, so now we've got, I would say, a decently equal scatter. It looks a little bit better now. The straight line still fits, so that's good. That didn't change. And then these data points aren't really clumped anymore. Here's another sort of feature of the data. It's not an issue, but these are all the crabs, the jellyfish, the jellies. These are all from Dengar Island, right? They were on average a lot smaller than the other ones, right? So there being like a big gap in between these two, it's not an issue. It's a feature of the data, which we can live with, especially if we mention that, which I just did. Cool. Okay, and then these are all decently equal scattered. Not a whole lot above the line as you go further out. There's more below the line. Can we live with that? Maybe. Looking at the QQ plot, the skewness might be a little bit, different than our last model. So let's go ahead and actually look at the distribution, just because. Cool. Zoom that in. So this histogram looks a little bit funkier, but I think that the tails are a little bit more consistent with each other. Enough, The biggest thing here is that we've got that kind of gap in the data that make things a little bit difficult to work with. But for now, given that the residuals now look a little bit better, and all the p-values are statistically significant, and it's not, nothing is so crazy different between this model and the last model, let's stick with model 2 here. So let me, cool. I've got this model back up again. So now we're saying that for every increase in x is going to result in some percentage change in y. So that's good. That's okay. All right. Okay, so what do? Oh, man. Gosh, so just a quick side note, a little non sequitur. I am baking some bread right now, and I think it's going to be done at the exact moment that this lesson is going to be done. And I'm so stoked about that. I'll put a picture of it in the somewhere over here. I'll put it right here. Okay, so anyway. Let's look at the coefficient table again, okay? So we've got width, that looks good, right? So for every 1 unit increase in width, y is going to change by some percentage, and then this coefficient will be involved in there somehow. We can trust that because the p-values are pretty low. Okay, and then we have this Fraser Island and then Salamander Bay. Where the heck did Dangar Island go? Where is it? Well, I'll tell you where it is. It's being used as a reference, okay? So remember when I was dragging Bubba all over the place, and I put him in Laramie and said, with reference to Laramie, Medbo Peak is 5,000 feet above, and then Jome is also like 3,000 feet above. That's exactly what we're doing here too. So we would say, on average, with respect to, or with reference to Dangar Island, Fraser Island is this much different on average. And then Salamander Bay is this much different than Dangar Island on average, okay? And it's a little different because we've log transformed it, but it works. It's the same sort of interpretation as incremental change too. So that's all right. It might be a little confusing. So let me kind of bring out old Microsoft Paint here, just to show you sort of what's going on in the background. So we've got okay, cool. So we've got essentially in R, we have our one column here, and then this is the location, right? L for short. And we've got 3 different locations, right? We've got let's see, Dangar Island. Again, writing with my finger, so cut me some slack. We've got Dangar Island. We've got let's see, Fraser Island, and then we've got Salamander Bay. Cute. Okay. So what it's doing in the background is it's saying, okay, it's making these 3 new columns essentially, and we can do this by hand too if we want it. But what's happening here is it's saying, okay, make a new column for each of the 3 levels, or however many levels we're working with. And then when Dangar Island matches the column name, we'll just put a 1. And if it doesn't match, it's a 0, right? So it looks something like that. And then same thing for Fraser, and the same thing for Salamander, right? So a bunch of 1s and 0s, denoting when it is matching and when it's not, right? Okay, so what's happening here is saying, okay, and we'll go back to the old model too. Okay, we'll go back to the model. Go back. Okay, cool. So what it's saying here is that if we wanted to write out the equation, which we will in a second, we would put in, if we're looking at Fraser, trying to say something about Fraser, we would put in a 1 for Fraser, and then use this coefficient, right? And then we would put in a 0 for Salamander, which whole thing would go to 0, right? So if I go back to the old paint, let me write this down. So the equation is length equals 1.96 plus, oh boy, 0.04 width, and then, yeah, plus 0.15, oops, 0.15 Fraser, and then, oops, 0.25. I'm being real lax with the rounding here, so don't email me. Cool. Unless you do have questions, then please email me. Okay, so if we wanted to look at, how does Fraser, on average, affect length, right? It would be with respect to the one predictor that we don't have in here, which is the Dengar Island, right? We don't have a coefficient for that because we're using that as the reference, right? So we would say on average, and this is also the log of the length, nothing too crazy here. But we would say on average, it's this much larger, right, than Dengar on average, okay? It's very important you keep the on average in there. That's why I'm saying it all the time. But then we would say, okay, this f here, this would just get 1 because we're looking at it. We're looking at, the equation for Fraser. This would go off to 0, right? And then we would get L equals, let's see, since this whole thing goes to 0.15 because we're multiplying by 1, that just gets added into the intercept, right? So that's going to be, let's see, 1.96, like 0.21 or 2.1. So it would be that plus 0.04 width. And that's kind of our new equation for Fraser, right? We would say that it's on average 0.15 bigger than Dengar Island, right? And we would do the same for Salamander Bay as well. I don't want to have the comparison to Salamander Bay, though. Sorry, that was a little aggressive. I don't want to have the comparison to Dengar Island, is what I meant to say, and I got distracted by how angry that came off. Sorry. So how do we re-level that? Okay. Let me get this. Do I need this anymore? I'll leave it up. Okay. So how do I re-level? How do I re-reference something? Well, let's I'm gonna put it up in here. Re-level. Just so when we run the model again, I won't have to type in all that stuff or scroll around or whatever. There's this function called relevel, and it looks something like this. Very cool. But what we need to do first is say what we want to relevel. And so I'm going into the data set, and I'm going to call in the location, right? So I use that $sign. I use this $sign here. And then it just go in, and if I hit tab, which I'll do right now, it'll bring up length, width, length, and the location, right? And I'm trying to relevel that. So then, whoops, I can just go in and then use the relevel function here. Can I spell? No. And then it gets 2 arguments. Okay, the first one being x, which will just put in the location, right? That's the thing that we're trying to relevel. And then ref, short for reference, is going to be our new reference level, which it has to match perfectly one of the levels as far as the spelling goes within the data. So I don't want it to be Dengar Island anymore. I want it to be Salamander Bay, we'll say. So I'll type in Salamander Bay and then do that. And let's see how the model changes. Whoa, look at that. Now we're looking at it with reference to Salamander Bay. And if, let me actually pull up the scatter plot too. Okay, and so that's really it, if you can believe it. So it's okay that we don't have all of the levels showing up in the model, right? Because we're using one as a reference. If you were to code yourself, and I've sort of done it here, a bunch of zeros and ones or something, and then include all of these into the model and leave this one out, you'll get similar results. In fact, you'll get identical results. And let me show you. I'm not going to show you how to do that because it's kind of a bit much on the coding side of things. But now you see you get the same coefficients, and it's using Sal as that reference level, and it's throwing these NAs, right? Because of what's defined as a singularity here. It's because the Sal, when you leave that in, it's going to perfectly predict the outcome. So it's just going to kick that out. And then still use it as a reference, though. Whatever, not a big deal. but that's it, right? So coming back to old Bubba here. So funny. So here he is, right? You can move the reference level around, right? And it's fine, right? You'll get slightly different things as far as coefficients go, but it's still going to maintain the statistical significance as well as the R squared, as well as all the other stuff too. Just the coefficients are going to be different. And that's that, right? So let me zoom Bubba in here. Good Lord. And there he is. So that's that. If you have any questions, let me know. But this is pretty much it for the whole categorical variable thing initially. Next week, we'll get into some stuff that's a little bit more, intricate, we'll say. But we'll worry about that when we get there. And for now, I will see you next time.